All right, folks, let's get busy and learn some new math. Section 11.7, polar form of complex numbers. Let's just go ahead and break apart the title of this section first. We have something new, which is polar form. We've been talking about that for a couple lessons now. A polar form is a location in space that's defined by r comma theta. That's a polar coordinates define a location in space, r comma theta. So that's something relatively new, and here's something relatively old, something we talked about last semester in college algebra. We didn't really talk about it a great deal, but enough that we should be able to apply some things to it now. Remember, a complex number is a number that has both a real and an imaginary component. And imaginary number, don't forget the imaginary number we learned was lowercase I, which equals the square root of -1. That is the imaginary unit. And I know when I write my i's, my lowercase I, it looks like a 2 with a hat on it. Just do me a favor and get used to it. Because when I write my little lowercase i's like this, it drives me nuts because, well, what if that, the top's not on it perfectly, so I can't deal with that, and then, I might be tempted to do something like this, draw a little heart on top. Oh, isn't that's just precious. No, I can't do that either. So I'm just going to draw my I like this. It looks like a 2 with a little dot above it, and just get used to it. Okay, let's move on. So z equals a plus bi is a complex number, and this is the real component. The a value is the real component, and then b times I is the imaginary component, and again I being the square root of -1. And what we're going to do now is we're going to define functions, a real function and an imaginary function, where the real component of z is equal to a and the imaginary component of z equals b. So these things as written, they're written like functions. The real function takes the complex number z and returns the real component a. The imaginary function takes an input of the complex number z and returns the imaginary component of b, or just the coefficient that is on the imaginary number part of the complex number. So that's just a quick review of complex numbers and what we've learned so far. Let's move into an example now. Z equals a plus bi is the rectangular form of the complex number z. Remember, rectangular coordinates are x comma y. Polar coordinates are r comma theta. So z equals a plus bi is the rectangular form of the complex number z. We're going to graph each of these complex numbers on the complex plane to the right. So this is a complex plane. It looks a whole lot like an xy plane, but it isn't. It is a complex plane because we're going to graph real numbers on the horizontal axis and imaginary numbers on the vertical axis. So let's try z equals 3. If z equals 3 is our complex number, that could be rewritten as 3 plus 0 times I. Well, that's just in the complex plane, that's going to be the point 3 comma 0. So I'm going to graph 3 comma 0 and label it as z sub 1 because that's the first imaginary number we're graphing. First complex number. So let's go ahead and do these other ones really quickly here. So there you have it. We have 4 complex numbers graphed in the rectangular on the complex plane in the form a comma b. So where a is the real component and b is the imaginary component. Okay, so let's move on. And we're going to come back to something like this in a little bit. On the back side of the paper, we're going to introduce a polar form of identifying locations on the complex plane as well. And just like this complex plane is analogous to x comma y, the polar complex plane will be analogous to our r comma theta form of a location in space. All right, so now it's time for some definitions. The modulus and argument of a complex number. So let's let z equal the complex number a plus bi. And we're going to let r comma theta be the polar representation of the point with the rectangular coordinates a comma b. So just like I was talking about above, we can graph a comma b in the complex plane. We could also identify that same location with polar coordinates r comma theta. So the modulus of z is denoted modulus of z with, looks like z in a big giant absolute value symbol, and that z is equal to r. So the modulus of a complex number is equal to the radius of the point in polar form. The angle theta for the complex number, the angle theta is an argument of z. Okay, it's an argument of z. The set of all arguments of z is denoted arg z. So I'd like you, when you say this, please say it like a pirate. Arg z. And that's enough about the argument of z. Let's move on. The principal argument of z is written as theta equals arg z. Notice now this one is capitalized, so we really have to emphasize the arg. Theta equals arg of z is the theta such that theta falls between negative pi and less than or equal to pi. So I want to talk about this for a minute. What the heck's the difference between an argument and a principal argument? Well, if the principal argument is theta, then any argument could be theta plus 2 pi k. Okay, so that would be the set of all arguments, whatever the principal argument is, plus 2 pi k. So now just another quick word here about the principal argument. For the principal argument, I want to just show you the interval on a number line of values that are acceptable for the principal argument, because sometimes we struggle as students to pick the right values and know what the endpoints look like, those kinds of things. So if I have to be greater than negative pi, I have to put an open circle there. And I can be equal to pi, so I'm going to put a closed circle there. So that's the interval that's acceptable for the principal argument of theta. And it's kind of interesting to think about this interval. Does this interval contain a complete circuit around the unit circle? Does it contain a complete circuit around the unit circle? Well, that is an interesting question, and it's one I'd like you to think about and perhaps ask me in class. Okay, let's move on. Example 2 says, for each complex number in the top row of the table, plot z in the complex plane and find the real component of z, imaginary component of z, modulus of z, argument of z, and arg of z, the principal argument of z. Okay, so I'm going to go through this first one in great detail and let you try the others on your own as I zip through them. Okay, so if we have the complex number 1 minus 3i, my real component is 1. That's going to be positive 1. My imaginary component is negative root 3. Okay, so plotting that in complex plane, it's going to look like that. The real component of that complex number is 1. The imaginary component is negative root 3. The modulus of that, well, that involves a calculation. The modulus of that is going to be the square root of a squared plus b squared. That's the Pythagorean relationship. So I have 1 squared plus negative root 3 squared. Let's see, that's 1 plus 3, that's 4. Take the square root of 4 and we get 2. So 2 is the modulus of that complex number. Keep in mind, modulus involves a square root, and a modulus is a distance. Okay, it's like a distance from the pole. So it's always going to be positive. Let's make a note of that. Always positive. And I know we talked in some of our work with polar coordinates that we could have negative r values. I think we're going to be keeping the modulus positive at all times. I can't think of any examples where it'd be negative, but maybe we'll see one in the future. But for now, assume it's always positive. Okay, so now let's talk about the argument of z, the family of arguments of z. Well, let's see, theta here I have to consider theta from negative pi to pi. So this is going to be my theta right in there. And it's got an opposite leg with a length of root 3, an adjacent leg of 1. So theta is going to be equal to the inverse tangent of negative root 3. And the inverse tangent of negative root 3 is negative pi over 3. For the family of arguments of this complex number, I'm going to say it's negative pi over 3 plus 2 pi k. Remember, we have to include multiple revolutions around the circle, but the principal argument is just negative pi over 3. So that's it. We got modulus argument and principal argument of the complex number 1 minus root 3i. Folks, I want you to pause the video. I want you to work through these next 3 examples on your own, and I am going to fly through them right now. There you have it, folks. We're done with side 1 of the notes for page 1, or part 1, excuse me, of section 11.7. I'm going to shut it down now and split this notes page into 2 videos, so stay tuned for part 1, video number 2.